showing up. I see hardly any of you brought pillows. That's always a good sign. Okay, you ready to run it? Okay, this is what we'll be talking about today. The definition of an accident, an event that has led to significant consequences to people, the environment, or the facility. So we'll see all of that today as we look at all of this. This is the last session. I'll start off. Will Shafer, our Army nuclear power expert, will do the second part, and then I'll pick up the rest. I hope we can finish fast enough so that there will be enough time at the end of the talk. I'll be talking about nuclear submarine accidents and then submarine accidents that were not nuclear, the Thresher and the Scorpion, particularly, and the Kursk. So let's get rolling here. They could have all been prevented, and we'll talk about it. But for want of a nail, a horseshoe was lost. For want of the horseshoe, a horse was lost. For want of the horse, a rider was lost. For want of the rider, the battle was lost. For want of the battle, an empire was lost. The thread of these accidents that we'll be talking about, many of them went that way. A little thing, the horseshoe nail, was lost, and then a disaster happened as a result of all of that. But everything we'll talk about today could have been prevented, and we'll see about that. Okay, they were a result of one or more of the following: inadequate design, inadequate location selection, inadequate operating procedures, inadequate maintenance procedures, inadequate operator training and retraining, inadequate operational supervision, inadequate management. So the first thing we're going to talk about was in 1957 in Ozyorsk in the USSR. And actually, they had problems well before that date, but this date was the significant one that led to them being included in the talk today. We'll talk about the Army reactor, the SL-1 accident. Then I'll pick up on 3 Mile Island, Chernobyl, Fukushima, radioisotope spills. There have been a lot of radioisotope spills. Some of them have been pretty widespread and a big problem. Some of them were very localized and not a problem, but they are an operational or a locational problem in where they happened and why they happened. Russian submarine accidents, I'll tell you more about that when we get there, of course. U.S. Navy nuclear reactor accidents. 0. Zilch. None. Okay. Ozyorsk. Ozyorsk was a closed city, and you remember during the USSR times, there were many closed cities that even if you were allowed to go to the Soviet Union, you were not allowed to go to the closed areas because they were afraid you might learn something or they wanted to hide something from you. So it was a closed city. It was a plutonium production site. It was a weapons grade plutonium production site, and they handled radioactive waste. So it was a weapons and nuclear fuel reprocessing site in the closed city. Second worst incident after Chernobyl for radiation released, and you've probably never heard of it. The third worst incident after Chernobyl and Fukushima for the number of people impacted, 10,000 people. But see, it was a closed city, and we would never have heard about it. And it was out near the Urals, so there weren't very many people out there anyway. 22 villages impacted, 20,000 square miles. Several lakes are contaminated. Lake Karachay is the most contaminated place on Earth. 2 years after Chernobyl, the Eastern Ural radioactive trace area was established. After they established the big closed area from nuclear waste problems in the area of Ukraine north of Chernobyl, they decided they better close this one off as well. And it was the party labeled the blame on the plant director and chief engineer for allowing a cooling system to fail with no corrective action, causing a 70-ton equivalent TNT explosion. So let's see what was happening out there. Chemical processing was more dangerous than in the West because in the beginning, nobody knew how dangerous any of this was. It was all new stuff, all new technology, all new metallurgy. Everything was new. In the Soviet Union, they had less concern about the radioactive damage to people and the environment than we had in the United States. They were doing fuel solutions. They were pouring stuff into casks to determine what the critical mass was. I told you way back a long time ago, experimentally determining what is the critical mass of a plutonium or a uranium critical mass, no matter how you put it together, experimentally is not a good way to figure that out. And so they had problems, multiple criticality accidents. That is, they poured the stuff into a container and poof, it went critical. And it didn't do a complete atomic bomb type explosion, but it would cause a problem. And they did several of those. They processed fuel and fission products. They were stored in an underground storage container. And it was, the vats had failure prone cooling systems. They needed to keep the vats cooled. Radioactive material, when it is decaying, it generates heat. Not necessarily a nuclear explosion, but it generates heat. And with sufficient heat, you can have a real problem. Waste products were dumped into the rivers, lakes, and the ponds around the site. Stored solutions got too hot when the cooling failed. Explosions equivalent to 70 tons of ammonium nitrate and acetates and a widespread radioactive contamination. So this is where it's located. You can see the big blue arrow on the left, that's Moscow, and the red spot over to the right, which is where the area was located. And it's near Ekaterinburg, which is where for a long while the Romanovs were buried. Okay, here is the picture of what it looks like. And you can see the Mayak site, which is the area where it was being done, and the lakes around, and the ponds and the rivers, and an ash disposal area. You can see all of that up there on the map. It was built in the mid-40s. They were trying to catch up. Physics was poorly understood by everybody because it was all new. Environmental concerns, very few. The hurried process to try to catch up to the West. Now, they had some good information when they first started out because just as soon as anything was learned at Oak Ridge and Los Alamos, it got over to the Soviet Union because of the spies that were there. This is the area where the problem occurred, and you can see the swath of where the radioactive materials were blown and deposited. So cooling system failed, explosion, lakes and nearby rivers contaminated. Somewhere in the bottom there is Lake Karachay. That's where they had a lot of the dumping of materials in those days. So here's what we learned about that. Haste makes waste. That's true in nearly everything you're doing. But in nuclear materials, it's really bad. Widely scattered contamination it's difficult to decontaminate. And we learned some of that here when we had some problems. And we'll see some more of that later. You can't throw radioactive waste away. There is no away. Storage of radioactive waste is a long-term proposition, and it's one of the major problems with nuclear power. Okay. Did I finish with that one? Let me see. Oh, laser. B, backup. Okay, I'm done. You're up, Will.
Don't get off with the tether.
Forward and laser.
Thank you. Thank you, Walter. Fortunately, in the United States, the growth of nuclear power was highly regulated by the AEC. You recall that it was 1946, the AEC was set up by Congress. And as we learned from what Walter just said, experimenting was not always the best way to go, but there was an awful lot of experimenting done in the early nuclear power plants, and we learned a lot of lessons the hard way. The AEC, naval reactors, and the Army Nuclear Power Program were the three entities that really shepherded the early days of nuclear power. Unfortunately, the Naval Reactors Program was very tight-lipped, very highly classified, and a lot of what they learned was not shared with the rest of us that were developing nuclear power, unfortunately. And I had some personal experiences along those lines. Basically, we were evaluating alternatives. The first major area of alternatives was core design, and we talked some about that in the past, but long life, safety, and basic design from nuclear considerations were some of the things they were wrestling with. Then we wrestled alternatives with systems, pressurized water reactors, boiling water reactors, gas-cooled reactors, that sort of thing. Then there were various applications that were experimented with. We're all familiar with the subs and then the surface ships that Walter's mainly concerned with. Then the DoD was mainly concerned with remote sites. For instance, for the Army and the Air Force up in Greenland or Alaska, the DEW early warning systems to help us with missile defense in the early days of the Cold War. Also, the idea of training plants became important. And then in the Army Nuclear Power Program, we had, I think, a total of 9 plants that were considered. One was never designed. 2 turned out to be never useful. The SL1 was one that I'll be talking about in a moment, and the NL1, remember the gas-cooled reactor. Those that were pressurized water reactors, 4 or 5 of them, generally were designed, adequately operated. We learned a lot from them and had a life generally of 8, 10, 12 years. The SL1 was a small land-based boiling water reactor, and we're up, okay. The reactor first went critical in October of 1958. So when we got around to the SL1's accident, it had already been operational for about 2.5 years. And it was a boiling type reactor, which really was not used much practically in the beginning. Casualties, 3 operators were killed. In this accident, there were 2 enlisted Army and 1 enlisted Navy that were at the accident scene, and all 3 died. We're very careful to say in the United States that there have never been any deaths in the commercial reactor applications in our country. That's true. But there were 3 in the early days, and they were all military. The cause was a single control rod that was removed too far, and the reactor became critical. And it was something that shouldn't have happened. Walter mentioned inadequate maintenance procedures. This is an example of that. Inadequate design, this is an example of that too. Let's see, here we go. This is the site of the SL1. You'll notice that there's a metal silo building there. The reactor, the primary system, was actually in that silo building. That did not constitute containment in the sense of pressure containment. It did contain some debris and radioactivity, but this was not a contained experimental plant. It was a very low-level plant, only 200 kilowatts electrical and 400 thermal, because it was intended for use in, say, in Alaska and Greenland, and just to run a small site. The cross-section of the core is shown here. Let's see. The T-shaped peripheral rods, as we mentioned. Is this thing working? Here we go. Rods 2, 4, 6, and 8 were around the periphery of the core on all four sides. The crucifix, or the plus-shaped rods, there are 5 of them. They were interspersed. And then one of them was the one right in the middle, rod 9. That was the central rod, and that was the rod that was accidentally removed too far and caused the accident. This shows a cross-section of the pressure vessel area of the plant. You notice the pressure vessel starts up here, it goes down, back up the other side. It has a cover. Through the cover of the pressure vessel are the control rods. And down here in the bottom, for 4, 5, 6 feet, is the active core. And out of the core are the control rods attached to the actual control rods that insert into the core to absorb neutrons, and then the mechanisms that raise and lower the control rods. Here's a motor that drives the control rods, and the control rods can be disengaged from the drive system and have to be re-engaged manually, and that's where the accident really happened at that point. Okay. The reactor was a highly enriched uranium reactor, 92.3% U-235. There were significant fission products because the plant had already operated for about 2.5 years. The reactor control rods had a history of sticking. This was a huge red flag. In my opinion, once that sticking took place, the AEC should have shut this operation down. The control rod number 9, the center rod, was disconnected from the control rod drive mechanism for maintenance. The control rods weighed about 84 pounds each, so you see it took a pretty hefty guy to get in there and bend his knees down and straighten his back and to lift and lower that rod the few inches it needed to be repositioned to re-engage it with the control rod drive system. A technician attempted to lift rod 9 about 4 inches to re-engage. The rod sticks a little bit. He couldn't get it up high enough. The technician, the Army enlisted man, jerked the rod to clear point of sticking, and rod 9 lifted on the order of 20 to 26 inches. And the SL1 went prompt critical, which meant it had a chain reaction, and it was increasing in power level, the power doubling about every 10 microseconds. 4 milliseconds later, the fuel melted and explosively vaporizes. The water hammer hit pressure head on the pressure vessel at about 10,000 psi. The water upward velocity was about 159 feet per second. The water hammer propelled the reactor vessel upwards 27 feet per second. That reactor vessel actually was very heavy, and you wouldn't think it would have moved. The shield plugs, these would be the plugs where the control rods came through the cover for the reactor vessel, were ejected at 85 feet per second. with 6 holes in the top of the reactor vessel, high temperature water and steam spray into the room with radioactive debris from the damaged core spread around inside that silo, and of course, much of it escaped the sheet metal. The reactor vessel itself was 13 tons, 26,000 pounds. It jumped 9 feet plus upwards, with parts striking the ceiling before it settled back down. So the control rods, which were actually up near the ceiling, actually penetrated the ceiling when the pressure vessel came up. The excursion, the steam explosion, and the vessel movement only took a couple of seconds. The spray of water and steam knocked 2 operators onto the floor, killing 1 and severely injuring another. And the number 7 shield plug from the top of the reactor vessel, this would have included the control rod, impaled the 3rd man through his groin and exited his shoulder, pinning him to the ceiling. A little bit gruesome. During the accident, SL1 designed for 3 megawatts, operated at 20 gigawatts, 6,000 times safe operating limits. It was estimated that 32 kilograms of TNT equivalent explosion, that was about half of that Walter mentioned for the Russian plant. Rescue crew meter pegged at about 500 Rankins per hour outside the building. I was trained in disaster recovery from nuclear power because I was the only one at McMurdo Station in Antarctica that had any disaster recovery experience should we have had an accident. I recall very vividly that if you are in a 500 Rankine per hour field and you're exposed to that for 1 hour, you will have picked up 500 R. That will give you the probability of about 50% mortality, fatality. And you can extrapolate from that up and down. 1 survivor of the crew of the 3 died in the ambulance on the way to the hospital. All 3 of those men were buried in heavy lead caskets, and the nurse who rode that ambulance picked up quite a few R. Here's a picture of the SM-1 core after it melted, and a good reminder lest we forget. Radioactive non-reactive metal debris was removed and buried near the site of the disaster. The reactor core was removed to the aircraft nuclear power hot shop for examination, and it was later placed in a cask. Manually operated high-power vacuum cleaners were used to collect small debris from the site. Radiation monitors were placed around the site. Higher capacity radiation monitors developed for quick response teams. Each person who participated in the disassembly of that building, the burial and so forth, would be given a stay time in a recovery site. And they were limited to probably 5 R per year max. Examination of the core indicates that corium, core meltdown lava-like material, which could melt through the pressure vessel, was not detected. So the disaster was somewhat limited, but who cares? It was a disaster. Okay, some of the accident causes: poor reactor component design. At this point, the core physics people, the physicists, kind of ruled the roost in nuclear power. There wasn't an awful lot of input by others with regard to core design. They particularly did not involve metallurgists and that sort of thing to make the core as good as it should have been. Inadequate quality assurance during manufacture, incomplete welds on fuel cladding, inadequate follow-up on frequent control rod sticking incidents. And again, I mentioned my opinion was that this red flag should have shut the program down. Reactor interior cadmium and boron poisons flaked or fell off. Cadmium and boron are neutron absorbers. They were built into the core to help control the chain reaction, the level of the reaction. And these were not, they weren't engineered properly, metallurgically and manufacturing wise. Inadequate supervision during special test operations. There was nobody in the control room of the plant when this incident happened. Looking at lessons learned, I sometimes simplify these a little bit in a different way, but first, the reactor design requirement that most reactive control rod cannot cause a criticality of fully withdrawn. One stuck rod requirement. This was a requirement in the Naval Reactors program from day one. If this were a requirement in the Naval Reactors program, why didn't the AEC, who designed this plant through Argonne National Laboratories, incorporate that design into this plant? You recall I mentioned there was not an awful lot of communication between Naval Reactors and the rest of us. The one stuck rod criteria means just that. If one rod is stuck outside the core, under no conditions will the core become critical. This particular rod was the one right in the center, which absorbed more neutrons than any other rod and was more important, really, than the other rods. It would have been the governing design criteria. The SL1 design was scrapped, rightfully so. The greater attention required for metallurgy of reactor components. So we're talking now in terms of specifications, in terms of the manufacture of the components and their assembly, and so forth. Detailed operating procedures prepared and mandated. At this point, the AEC required operating procedures be in minute detail. However, maintenance procedures were sketchy and not really required to be detailed. After this, maintenance procedures were given as much review emphasis as operating procedures within the AEC. Required additional shift supervisors for unusual evolutions. Remember, I mentioned none of the three on duty at that time were in the control room. Oops. Okay, also I'd like to mention here that after this accident, then it was required that one person on the crew be in the control room at all times. And also at that time, we added Big Brother, or an audible or visual pickup of what was going on in the control room, usually just an audio, so that any commands, discussion, et cetera, were recorded for posterity. So probably the one stuck rod criteria, the maintenance procedures, and the Big Brother and manning the control room were the three big lessons that the AEC promulgated after this. Over on the right is Idaho Falls, and you can see over State Route 20, maybe 40 miles, was the SL1 site. And at the site, there's a suitable monument to the SL1. It was a plant that probably should not have been built the way it was. It had a service life of 2.5 years before the incident. We did train quite a few people there. The incident took place in 1961. And in 1961, I was just preparing myself to get into the nuclear power program, so it preceded me a little bit. Although I did have several friends who were training at the SL1, one who was there at the time of the incident, but he was on leave with his family. But anyway, Walter, I think that exhausts the SL1.
Okay. Thank you very much, Will. That was great. And that is the only reactor accident in the United States that resulted in immediate death of any operator or personnel assigned. Okay, we're going to go now into 3 Mile Island. We were all alive and aware of the time that that happened and when it happened. It was near Goldsboro. I'll show you a map. I showed you a map last week of where that is. There were no direct casualties. And the cooling system failure, and this is going to be one of those loss of the nail deals. Okay, 3 Mile Island is southeast of Harrisburg. It looks like this, the reactor containment buildings. Will mentioned that the SL1 did not have a containment building. This is the same Babcock and Wilcox design as the Crystal River complex, single reactor. In Crystal River, these two stacks that are there for the coal-fired plants, not for the nuclear plant, was cooled by Gulf water. That containment building was designed to accept without damage to the systems a straight-on impact of a 707, which was the largest planes that we were flying at the time. So it's several feet thick of concrete and reinforced steel. And there's outside, I don't think we can see it on here. Let me get over closer. But there are tension wires wrapped all the way around that containment concrete building, and they are tightened up to a specification to keep everything contained. Okay, there's the airport, just another view of the reactor. Okay, this is going to show us the accident, so keep a watch down here on the blue pump. The blue pump is shut off. Now there's no water, feed water going up into the reactor to cool the reactor. The reactor's still running. When that shut down, the steam turbine shut down. Later, there was cavitation because there was depressurized. Early on, the pressurizer blew, and there's water and steam in the reactor, and that's basically the sequence of what happened. Let's go into it in detail. If you look up at the top at my blue arrows pointing down, you'll see the big red thing is the pressurizer. The purpose of the pressurizer, as we talked about last week, was to keep the water in the reactor at a pressure higher than the boiling point of the temperature of the water in the reactor, to make sure that there was no steam anywhere in the reactor and you could get very good heat transfer from the fuel rods into the primary coolant. There are two other arrows up there, pressurized operated relief valves. What happens there is they have a valve, it's got a diaphragm on the bottom, it's a set point. If the pressure gets too high, it pushes a dog. I don't know, that dog died during this incident. Okay, so the reactor built pressure operated relief valve. If the pressure gets too much, little valves will open and they should shut when the pressure goes down. They didn't do that. The safety valve on the very top of the pressurizer did not go off. It had a higher set point in pressure than the pressure operated relief valves, which were supposed to allow you to drain some of the water into the pressurized relief valve tank there. Okay, now in the lower bottom, you see a secondary non-nuclear part, but up here, this is the main feed water pump. This is taking the condensed steam, putting it back into the reactor to make more steam. Now, not shown on this diagram are a couple more pumps. The emergency feed water pumps would go in there, and we'll talk about that in a little bit. So how did all of this happen? Why did it come about that this thing could happen? Okay, there was a failed attempt to clean condensate polisher. That's a fancy name for a filter to make sure that there's no particles that are going to go into the reactor that could mess up the flow inside the reactor. It was an attempt to clean it, and the way they did that is the same way we used to clean some of our pool filters. You backflow it and you flush out the bad stuff. They had problems doing that, so they tried an unapproved procedure. They blew air underneath it to try to get the crud blown out and restore that polisher. There was more than one polisher, and some valves or some pipes didn't have that, so it wasn't a single thing that would have completely caused the problem. air in the instrumentation line from when they were trying to blow the crud out of the polisher shuts down the condensate and feed water pumps because it thinks that there's no flow going to them. What happens at that point was an automatic scram or automatic shutdown of the steam turbine, which led to an automatic scram of the reactor. The reactor had been operating for some significant length of time at 97% power. As I mentioned last week, when you have a nuclear power plant providing electricity, you want it to operate at full power all the time because it's the cheapest electricity you're going to get on that day. So steam turbine shuts down. The reactor shuts down from 97% power. Emergency feed water pumps, which would have provided more feed water into the steam generator to keep the reactor cool, they started automatically just like they were designed to do. But from recent maintenance, the shutoff valves for the emergency feed water were shut. And so you turn the pump on, you get pressure, water doesn't go anywhere. The reactor heat now, because we're not putting feed water in, we're not making steam, the steam is not taking the heat from the reactor. The reactor causes heat, and a reactor, when you shut it down, will still provide heat at 6 to 7% of the power at which you were operating at the time. So if you're operating at full power, you have a 1,000 megawatt reactor, and you shut it down, you're going to get 600 or whatever the number comes out to be. 6 or 7% of the full power is still being generated as radioactive heat from the fissions that you caused while you were operating. You can't get the heat out now because there's no cooling water coming into the steam generator. The pressure operated relief valve opens and fails to reseat. A failure. The coolant escapes through that tank as steam into the containment of the reactor. The main coolant pump shut down on cavitation because when you reduce the pressure in the pump, it's like if you start up your motorboat and you floor it right away, you'll see the air bubbles trailing out from cavitation. So when the pumps are cavitating, they're designed and they did shut down. The core overheats and a partial meltdown occurs. 20 tons of melted fuel residue are contained in the bottom of the reactor pressure vessel. The rest of the 68 tons remained in the core region of the reactor. No significant residual health problems from radionuclide leakage. Nearby dosage equivalent to about 1 chest X-ray, which is around 100 millirem, more or less. All significant radioactive particles, including the melted fuel contained in the reactor pressure vessel. This was not the China syndrome. The fuel did not melt through the bottom of the pressure vessel. Remember, the pressure vessel is probably between 9 and 12 inches solid stainless steel, welded everywhere. So it did not go through the reactor pressure vessel into the containment building. So what caused this? Failure of the main feed pumps at 97% power, and I told you why they failed. The feed pumps themselves did not fail. They shut down as they should have because of an error indicating that there wasn't water flowing through them. The turbines in the reactor shut down as it was designed to do, but the residual heat increases the pressure. Its residual heat, 6, 7, 8%, increases the pressure. Pressure relief valve opens, but fails to shut down, but it indicates shut. And that was another problem for the operators. They thought that the pressure relief valves had shut, meaning that the water was contained and the pressure was contained, and the pressurizer water level indicator indicated there was still water and steam in the pressurizer, which implies that there's no steam in the reactor itself. It implies the reactor is still full of water and therefore is not going to melt down. That was untrue. The emergency feed water start as required, but the valves were shut. Pressurized water level erroneously indicated level normal, indicating, as I said, the pressure vessel is still full of water. Main coolant pumps cavitate and they shut down on a safety procedure. Operators stopped adding primary coolant because they thought with the pressurizer showing the water level in the pressurizer was normal, which was not. They assumed, and you know, if you assume, it makes an ass out of you and me. They assumed that the primary coolant was not needed. The pressure vessel was still full of water. But the steam gathers in the reactor vessel, and this is a real problem. Steam in the pressure vessel, steam and zircaloy create hydrogen. The hydrogen can explode. It did not explode here because it was contained in the pressure vessel. So this is just a picture. It shows you where some of the stuff is. Some meltdown and some slag and some other problems with the pressure vessel, but everything is contained inside the pressure vessel. The radioactivity from the fission products is not exposed outside of the pressure vessel. Okay, here's what we learned. Partial core meltdown, but it was contained in the pressure vessel. Steam and zircaloy create hydrogen, but it's within the reactor pressure vessel. There's no oxygen in there, no hydrogen explosion. A minor release of radioactivity gas from the coolant system as it continued to boil and send that water and steam into that overflow tank. It's all contained basically inside the containment. Psychological panic among the population, because I believe that the China Syndrome movie had come out before 3 Mile Island. And everybody said, oh my God, we're going to melt down to the center of the earth. 13-year study of 32,000 people found no adverse health effects, such as cancers, that could be linked to the accident. It took 12 years for the final cleanup and deactivation of 3 Mile Island 2, which was the operating reactor that failed. Cleanup cost almost $1 billion. 1,000 workers were participating in the cleanup. Fuel residue remained underwater during defueling, and they were able to keep the water in there to keep it from overheating again. Defueling into 342 fuel containers shipped off to Idaho for long-term storage in concrete vaults. 10 megaliters of contaminated water, that's like 2.5 or 3 million gallons of radioactive water. And what are you going to do with that? Well, you store it and you evaporate it until you have not 2.5 million gallons of water, but you have radioactive residue. 1% of the fuel remains in the reactor vessel on site today. What did we learn? Reactor plant operator training was inadequate. Reactor plant operating procedures were inadequate. Reactor plant operators required emergency training. Institute for Nuclear Power Operations was created. That is a semi-private organization, mostly consisting of Navy nukes and other qualified nuclear plant operators. And it's modeled on the Navy Operational Reactor Safeguards exams, the ORS. We had ORS exams on all Navy nuclear ships every 1 or 2 years. These guys come in and they throw a whole bunch of accident type things. My submarine, the big problem that we were given was a fire in the lower level engine room, bilges from oil. And then what do you do to protect the reactor? So, but they come, and if you're starting up from shut down from a shipyard, you have to have an ORS exam before you're allowed to start up. And if you don't pass the ORS exam, some of you get fired. I had an admiral tell me, "Hey, Walt, you want to have a successful command tour in nuclear submarines?" I said, "Yes, Admiral. Keep firing your engineer till you get a good one." Okay, when the ORS team, or when now INPO comes, they're going to give exams very much like we had in the nuclear Navy. Knowledge of performance of plant personnel, we had written exams, we had oral exams, and they examine the condition of the systems and equipment, quality of programs and procedures. In the nuclear Navy, if you wanted to start up the reactor, you had the engineering officer of the watch sitting there with a reactor plant manual in his lap, and it went step by step on how you would start up the reactor. If you had an accident recovery procedure you needed, you flipped a different part of the reactor plant manual to go through the approved steps for recovering from that problem. The effectiveness of management was examined. I don't know what the 8% is for. It's left over from another slide. Okay, so that is 3 Mile Island. Let's go on to Chernobyl. We all remember Chernobyl. I don't, how many of you have seen the Amazon Prime series on Chernobyl? There's a couple of you. It is an excellent series. It's very, very well done. I think there's maybe between 4 and 6 episodes, and it starts with everything operating normal, and then they have helicopters flying. They went through the whole procedure, but it is very, very well done. Okay, it's in Chernobyl. I'll show you in a map in a minute. It's north of Kiev. It was a boiling light water reactor, but it's graphite moderated, not water moderated. And you'll see a minute that the pressure tubes surround the fuel control elements, or fuel elements. And it was a low percentage of U-235. Casualties, one guy died immediately, and lots more died before too long. It's a flawed design. It was poorly trained operators. There's a test procedure that they were going to do, but it wasn't followed explicitly. And there's no containment building on these RMBK reactors. It's a concrete enclosure, but it's not a 5 or more feet concrete with internal and external steel rods. But the test procedure that they were going to do was it was a good thing to run. What they wanted to know was, if you had the reactor scram and you're still making steam, but you're shut down the reactor, you're making steam, is there enough steam left to keep the reactor coolant pumps running until the diesel generators have time to crank up and take up the load? So that it's a good idea to find out if that works, but they did it very poorly for several different reasons. Okay, here's where it is. It's north of the big blue arrow on the right is Kiev, and it's up north where the red button is. And you can see it again on the other chart. And north of the site is where the Palyaski State radioecological reserve has been established, and everyone was moved out of there. That's very well shown in the movies by Amazon Prime. So this is what the reactor looks like. You see a concrete shield surrounding everything. There's not a concrete shield going over the top of the control rod area. The control rods had to be operated through there, and you have pumps in the bottom. They're circulating pumps. They're not primary coolant pumps. They're just circulating because you want to keep the water flowing through and get the steam out through the top. And here's another view of it. So the hashed marked area is the graphite moderator. The fuel tubes, you can see the water flows up from the bottom through the tubes where you get steam out at the top, and all of that mess goes into the steam separator. So there's some water in there, there's some steam in there. And what you want to do is get steam out the top, run it through the turbine, and get your primary coolant pump, the feed water pump, running and get the water back in. In this case, it's being pumped into the steam generator from the bottom, and then the circulation pumps will circulate the water through the fuel rod areas. And you can see control rods. You see the steam flow. But this is a way, and there's a number of these reactors in what used to be the Soviet Union and is now Russia. So what happens in the sequence of events here? The test had been done before without problems. So they thought they were just a routine test we're going to do. We're going to shut down the reactor and see what happens. But some other guys came along and they wanted to do some tests before they got to the test about the steam recovery enough to keep the pumps running until the generator kicks in. This reactor has a positive void coefficient. So more steam, it's positive, the power increases, and it requires control by the operators and the operating system. It had been running near full power before the test. Again, now, if you're running at full power, you get 6 to 8% of residual heat generated from the fission products decaying after the fission has stopped. The reactor power for some other test procedure was reduced below the test power of the test for the steam residual operation of the coolant pumps. So they deviated from this procedure that was established to run the steam test itself. Xenon 135, we haven't really talked about that. I may have mentioned it in passing. So Xenon 135 comes from iodine 135, which is a few percentage of the radioactive products of fission are iodine 135, has a half-life of a number of hours, 8 or 9 hours, and it decays into xenon 135. Xenon 135 sucks up neutrons like a sponge. It is a poison. So when you shut down from full power, you have your iodine still building up. If you're running at full power, you just raise the control rods a little more to keep more reactions going, so you're not losing your neutrons into the xenon. But you can operate with that xenon there, and it'll become a steady state amount of xenon, and it's about the most that you're ever going to have because you're operating at full power. So when you shut down, you have the iodine still building up a little bit. The xenon is running at a steady state, but as it starts to absorb the neutrons, it goes a little bit down, but the iodine's still making more. So you get a buildup of xenon 135, and they had that happen to them. So they raised the control rods in the reactor more because now they had to go from like 30% to 50% to run their test, which they had done before successfully. So they figured, we'll just run the reactor back up to 50% and we'll be okay. The pumps were operated per the test plan at only 50% of the pumps. So that was part of the test procedure for the steam test, not for the other test. The pumps turned on and cooler water goes into the reactor. Cooler water is a more active moderator the reactor plant began to increase in power. The steam void increased the power excessively. Reactor prompt critical, resulting in fuel elements rupture. And when we were looking at the SL1, you remember that the power was doubling on prompt critical every 2 to 4 microseconds. And in 4 milliseconds, the SL1 blew up. So if you are prompt critical, you are increasing power exponentially at an uncontrollable rate. The pressure tube top plate blew off. It's not in a containment building, so now you have the top plate blown off. The fuel rods melt down. The roof is blown off because this was just a roof, not as strong as what we have here at Oak Hammock. It's probably just a stainless or tin roof or something equivalent. It's blown off, resulting in a major nuclear accident because everything is now open to the atmosphere, and you had the reactor blow up. You're in deep trouble. On the right, you can see sort of what it looks like. The roof has fallen down into the reactor a little bit. It got meltdown. It's blown residual stuff up into the upper area. Helicopters flew over this open, fuming reactor to drop in neutron absorbent to try to shut down anything that was going on. A number of the helicopter pilots died of exposure to radioactive particles. So here's the causes. Poor design, positive void reactivity, positive cold water reactivity, there's no containment building, failure to follow detailed test procedures. Had they followed their test procedure and brought the reactor to a half power as the test procedure called for and run the test, there never would have been a Chernobyl accident in all likelihood. Safety systems were shut down for the test. That, I think Will and I both agree that's a stupid idea. You never should shut down your safety systems. Xenon poisoning, I mentioned that, caused excessive control rod withdrawal to increase power level to the test level. Restarting more pumps added cold water, big time problem. So immediate high radiation at the reactor site, really high radiation levels. The roof was blown off, fire and explosion released smoke and radioactive particles, particularly cesium. I can remember in the 60s when the US had stopped testing in the atmosphere, the Russians were testing in the atmosphere, the Chinese tested in the atmosphere. At the reactor building at Cornell, we had to swipe down packages coming into the reactor because some of them were more radioactive than were allowed to be released from the building if we had had some radioactive waste. So there were problems in the 60s. Prevailing winds spread the high radioactivity over northeastern Europe, low radioactivity over northern hemisphere. 2 operators killed in the first and second day, if not more, because there was not a lot of transparency from the Soviet Union of the operations at the time. 30 killed within 90 days because they had firefighters race in and they were wearing their full firefighting gear and they were just absorbing radiation as they were trying to get close enough to the building to run the hoses to try to put out the fire. An estimated 4,000 long-term radioactive sicknesses and deaths in the Ukraine, Belarus, and Russia. Estimated 16,000 long-term issues in Europe. Estimated 60,000 long-term sicknesses worldwide. So let's see a map of what's going on. And this is a top-down view on the left of the northern hemisphere. And the yellow indicates different areas where there was radioactivity detected. You can see the red very close to Chernobyl. That was very close to when the accident happened. And there were radioactive particles spread around in the northern hemisphere. Looks like not to North America, but here we go. So there's now a spread of high radiation areas, medium and low, around the Ukraine, and then over the top of Russia and the northern countries, Finland, Sweden, Norway, are very close. Okay, the cleanup, short term, firefighting Unit 4 and Unit 3 roof. Firefighters got high doses of radioactivity. There were 4 or 6 plants at the Chernobyl site. 2 of them are still running, but there were damage to Unit 4 and Unit 3. Firefighters with high doses of radioactivity. Helicopters dropped in neutron absorbent, as I mentioned, sand and clay. Pilots got high doses of radioactivity, trying to hover right over the site and then drop the stuff exactly where they wanted it. Later, they did flybys and dropped whatever they had, and they hoped it went where they wanted it, but it prevented some of the helicopter pilots from getting the high doses of radiation. First responders entering the building, they're among the 30 or so people that died within 90 days. They shut down most of the RBMK reactors because they had the same design as Chernobyl. The long term, they encased Unit 4. I'll show you a picture later. And that's really well done in the movie. Established radioactive exclusion zone, 30 kilometers long, 2,800 square kilometers. 350,000 people are relocated from the area north of Chernobyl. They redesigned the RBMK reactors to take care of some of the technical design problems. So here's what we see. This is what's left of it. There are at least 2 other reactors you can see in the brown and or gray and white striped buildings, but Chernobyl number 4 is on the far right. And they could not bring contractors in to build this building to cover up the reactor. They built the building a few hundred meters away on railroad tracks. They had the building built the way they wanted it, and they rolled it in place. And then I think they've added more concrete into the enclosure that we see there, the Quonset hut. The stacks are normal around reactor plants. It's for release of gases that you might run into. And there you get some radioactive release. Okay, Chernobyl, lessons learned. Xenon poisoning must be taken seriously. Detailed procedures are needed for test procedures, and they must be followed to the letter. They stopped RBMK design, reactor and new construction. Accident response plans are needed. They didn't have any. This was all a big, terrible surprise to them. High-level radiation monitors needed. The same with SL1 reactor. When you go in, we had little portable radioactive detectors, and they're good for like 100 rem, maybe. We're talking thousands of rem, radio Roentgen equivalent man is the term. But they needed some that would go up to 1,000 or more rem to find out how bad it is. If you go up near something that's radioactive and your meter pegs, you don't know what's there. You know it's more than that, and you probably ought to get out of there. Containment structures are needed for the RBMK reactors. Okay, now we'll move on to Fukushima. Everybody remembers that because it happened recently, 2011. These are the GE boiling water reactors. Casualties, no direct deaths. 1 worker died of exposure later. 2,000 deaths total. The cause was an earthquake-induced and tsunami of 14 meters. And we'll see what that looks like. Here's where Fukushima is. Tokyo is in the bottom right. And Fukushima is up there where the red spot is. There are 6 reactors at Fukushima. They're all GE Hitachi boiling water reactors. And 1, 2, 3, and 4 are down at where the damage is. 5 and 6 are up, and they were not damaged. They were not involved in the problem. Okay, here's what we have at Fukushima. You have the normal water level over there at number D, average sea level. Then 10 meters, 4 meters higher, you have some ground level, and another 10 to 15 meters higher, you have ground level. And then where A is shown, those are power station buildings. So the B level is where this tsunami went. And this is just another view of it. You can see 1, 2, 3, and 4 are right down near the shore. 5 and 6 are located a little higher over to the right of the picture. So this is, again, I showed you this before. This is the boiling water reactor by GE. And it has coolant recirculation from the condenser. Steam goes out the top to the turbines, just like all the others. This is a different picture. You can see a little bit more of the design with the wet level below and the secondary containment. The primary containment surrounds the reactor. Control rods come from the bottom, which means you can refuel it without having to worry about the control rods. You leave them fully inserted. You take the 2 top caps off, and you can get at the fuel with the crane that's in the overhead area, and there's a spent fuel pool next door and within the containment where you can put your spent fuel. So it's an efficient design. I'm partial to pressurized water reactors. But there's a lot of these around the world now. All of the ones in the US that are boiling water reactors are the GE design. So here's what went on. The earthquake happened. The reactors that were operating were automatically shut down based on the earthquake. So 1, 2, and 3 are shut down. Reactor 4 was undergoing refueling. It was not operating. Loss of power to the site. The diesel generators, the backup power to run the pumps, started up as they were designed to do. The 14-meter high tsunami arrived shortly after the diesel generator started up, and it flooded some of the area that was involved. It didn't flood the diesel generators. They were high enough up, but it flooded some of the switchgear that sends the electrical power to the pumps, and so they were shut down. Lower parts of reactors 1 through 4 are flooded because the buildings were not designed to be swimming pools, so they got flooded. The diesel generator shut down on losing power, and therefore losing power to the circulating pumps. 3 nuclear meltdowns, 1, 2, and 3. 3 hydrogen explosions because of the radioactive contamination was spread around inside and outside the reactor buildings. The hydrogen explosion happened just like we talked about before. Steam with the zircaloy and extremely high temperature releases hydrogen. In this case, they were not contained within the containment building or the reactor vessel itself, and there was oxygen in the buildings, and it exploded. Unit 4 spent fuel pool heats up because they were doing a refueling there, but it did not heat up to a sufficient amount to cause a problem. No boiling, no exposed fuel elements. But emergency diesel for Unit 6 remained online throughout the problem. And it also picked up the power to Units 5. So 5 and 6 were not significantly damaged by anything. Now, the other problem that happened, they lost all power to the site from the Japanese electric power plant. These guys, these reactors were generating power and putting it on the grid for Japan. When the reactor shut down, they lost external power for some reason, and so they couldn't run the generator or the reactor coolant pumps from external power. They're designed to run on the generator from the diesel generator, but again, they had a failure there. At some point, seawater was pumped into the buildings, and we probably remember seeing that on TV. These things are still hot. They're a problem. We need to cool them down, flood them down with seawater. Okay, accident causes. Site design did not protect the emergency diesel generators. Oh dear, we're running along here. So they shut down. So it was another problem. Recommended upgrades to the site were not implemented. Reactor emergency cooling design was inadequate. Components were in flood-prone areas. Reactor earthquake protection SCRAM worked properly. Reactor shut down automatically. So extensive damage and meltdown 1, 2, and 3. Hydrogen explosions. Major damage to building 4 because it was connected through the air conditioning systems to unit 3. It got hydrogen in building 4, and they had a hydrogen explosion there. 5 and 6, relatively unscathed. Significant localized and area contamination. Nuclear fuel melted through the reactor pressure vessels and into the containment building. This just shows various levels of radioactivity around. This is the building 4. It had a hydrogen explosion, but it did not have a nuclear incident because it wasn't operating at the time. And if you see the yellow dome in the back, that is the pressure vessel top. And there's another dome back there on the left of that, a little gray. That's the steel dome that covers the top of the pressure vessel itself. That gave them access to an overhead crane, which has been blown up and gone somewhere else, to do the refueling. The reactor, you can see the cylindrical part of the building down below. Okay, here's an IAEA inspector looking at the damage of building 3. These are the areas surrounding Fukushima where they were required to do movement of people, studies of radioactivity, and so forth. The concentration of the air, you can see now the air was blown all around, and it looks like one of the highest levels of radioactivity, other than in Japan, was, I think that's probably Hawaii there, where the star is. So there was a great deal of radioactivity blown around by the winds. Okay, the cleanup. Several inches of containment topsoil is being dug up from the area. High pressure spray of structures with contaminated water collection. They were trying to spray them to solve the fires and to get water into the reactor containment buildings. They installed an ice wall underwater to isolate the reactor control contaminated water from the groundwater that would otherwise be able to have contaminated water from the reactor site flow into the groundwater. Okay, it's going to take 30 to 40 years to decommission these plants, tens of billions of dollars. Continuous monitoring of the vicinity, ocean water, ocean bottom, air and water, agricultural crops, seafood, and the groundwater. So the lessons learned: isolate and protect from flooding the emergency generators, power switching units, emergency coolant tanks, and pumps. Reduce the number of reactors in close proximity to prevent multiple simultaneous accidents. Locate the reactors further away from the ocean. Increase training of the management and the operators. Again, okay, there's been a number of radioactive spills. I'm going to just leap right through this and tell you that there have been some, and they're generally, none of them are as bad as any of the accidents we've talked about today. Happened some in the UK for their gas-cooled reactors. Most come from fuel reprocessing plants and plutonium separation. at least 2 incidents from leaks from submarines, contaminated water transfers to shore-based facilities. We had a gooseneck that you would screw to the overboard discharge from the high-pressure reactor area, and we had purifiers that were deionizers. We would pump the beads out to the tender for their storage and let them worry about the radioactive product problems, put in new deionizer beads. And so a couple of times there were leaks while doing that transfer. Okay. Most of the, well, you can read that. Some a minor amount comes from outgassing at nuclear power plants. Radioactive particles from nuclear plants, generally less than radioactive particles from coal plants, because coal has in it some radioactive particles as the process of making coal. This just shows all the stuff that gets into your body, whether it's internal, external, eating food, breathing bad air. Okay. I can run for another 10 minutes if that's okay. Okay. Hearing no objection, the chair rules. There have been at least 7 Russian submarine reactor accidents. 6 involved radioactive leakages. 4 involved multiple deaths on board. At least 2 submarines were lost as a result of that. 3 submarine crews had significant radiation exposure, probably resulting in later deaths. The Soviet and Russian submarines were not designed to the same level of protection of the crew from radiation as the U.S. submarines and surface ships were. Russian submarine accidents, radiation shielding was not as good as we had. Frequent submarine personnel suffered radiation exposure during their operation, normal operations. It's anecdotal, but there are stories that come from later crew members who were able to tell something about what they went through. Okay, submarine accidents, not nuclear submarine. They're nuclear submarines, not lost due to a nuclear accident. The Kursk, we all remember that. Some of you know the Colliers, Pat and Don Collier. Their son-in-law is a captain in the Royal Navy, nuclear trained. And I asked him, had he been involved in anything regarding the rescue of the Kursk? He said they were sitting on ready. The Russians never wanted to admit they had a problem until it was too late, and all the crew members left on the Kursk. The Kursk went down and off the north coast Russia, not far from Murmansk, due to a suspected torpedo explosion on board, a non-nuclear torpedo explosion. I've seen the Kursk, and I showed it if any of you saw my talk about a cruise that took us to Murmansk. They have a display there as the front part of the sail of the Kursk, and it's on display at the site in memorial of submariners lost. A Yankee-class sub, that was the first Soviet Polaris missile-type submarine, looked like an exact copy of ours, sank suddenly while being towed. A Mike class, the Soviet submarines were designated by some alphanumeric thing, which had nothing to do with the Soviet designation for their submarines. This one sank with a raging fire. The K-159, a November class, that was the first class of nuclear submarines that looked like our submarines. It went down in 2003. A storm ripped it away from the pontoons necessary to keep it afloat. Okay, 6,200 years of accident-free operation in the United States Navy, over 67 years, 144 million miles in 81 nuclear-powered ships, 526 nuclear reactor cores. Aircraft carrier started out with 8 nuclear reactors. One of my instructors claimed the privilege of having an 8-reactor scram. He shut everything down. They went now to 1 or 2 cores in the aircraft carriers. 150 miles steamed. Okay. So there were 11 aircraft carriers. The service life is extended of the ship as well as of the reactor system. One refueling maybe in as long as 50 or 60 years. Design is increased considerably. Okay, I would like to talk about the Thresher, the loss of the Thresher. 593 class, she was the lead design submarine of what would have been the Thresher class and was changed to the Permit class after the Thresher was lost. The Thresher had gone out. They'd finished some shipyard work. They'd gone out to do a deep dive. You can find unclassified information that these submarines can dive to 1,300 feet. The deep dive was designed to find out if there were any leaks, and there were. They attempted to blow the main ballast tanks. There were a number of operating procedures that got significantly revised. In those days, if the reactor scrammed, you shut the main steam stop to retain the heat in the reactor for immediate startup again. If you're at 1,300 feet and you shut the main steam stop, there's no main turbine to give you propulsive power to drive you up, which is what we always wanted to do. If we were having a leak, you put that sucker in full speed ahead and go up. They changed that as a result of Thresher. I had some friends and a classmate or two that were on the Thresher. When I was XO of Tenosa, we went through an overhaul at Portsmouth Naval Shipyard. We went out to the same area to do the same test procedure that the Thresher had done, but by then there was a thing called SubSafe. Every piece of equipment that went in the seawater on the submarine was tested, and you could check its origin almost back to the ore that was extracted from the earth somewhere. It was very well documented that this is a SubSafe article. You can put it in a SubSafe system and it'll be good. I wrote the test procedure for our operations on the deep dive, and we had listed every valve and component, every seawater penetration into the submarine, and they were all inspected and reported back once we finished all of the tests. Then we had to do an emergency blow. Now, what happened with the emergency blow of Thresher? They did an emergency blow. That's 4,500 pound per square inch air blown straight into the reactor tank. What happens when you blow air through an orifice? It gets cold. Those valves froze up and the air did not get into the main ballast tanks. Those valves were redesigned, and we added a water extractor and the air compressor output to have drier air in our tanks. And all the times that I've done an emergency blow system, we blew well and we came back up to the surface. Okay, so then we have the Scorpion. Scorpion was lost over near the Azores on its return to Norfolk, its operating home port. It failed to report in. When we were not on a special operation with radio silence, we had a system, we had to send a check report. And all it said was, from USS Tenosa 2, ComSublet, check 24. If you didn't receive one of those, that started emergency search procedures, because if you didn't send a check 24, it's most likely you got a real problem. So anyway, skipjack class, I've ridden on a skipjack class, they're fun. Most likely due to an electric torpedo failure. We had problems with those. They had to be recharged periodically. When you recharge a lead acid battery, what do you get? Hydrogen. And so there were problems with those, and that's what I suspect. For the Thresher, I'm pretty sure it was a failure of the auxiliary seawater system in the auxiliary machinery space on the lower level, which sprayed salt water at very high pressure all around the place. The switchgear was designed to be ventilated from the bottom. It sprayed water up. It shut off the electrical power. It scrammed the reactor, and it just got worse from there. Ever since then, every joint in an auxiliary seawater system and the main seawater system had to be ultrasonically tested, 100% coverage for at least 80% of the entire weld, which would be maybe 2 inches long. So it's silver soldered, 100% tested. There's where the sunken submarines are. You see the Scorpion lower right, Thresher up near New England, and the Soviet submarines, and there's some more over in the north of Russia. I think we're done. Finally, I'm sorry to keep you over time. If there are any questions, there can't possibly be any because I know I answered all your questions.
There might be some for you too, Mr. Shafer. I know that Bob Bernstein has some.
You wore everybody out.
Pushpa
Pushpa.
and Paula.
Okay, we have one from the Oak Room, and then Bob, if you'd like to unmute, we'll get you in a minute.
I just have a comment that in the movie for Chernobyl now, or at least when it was made, they actually showed that animals are returning there. They showed deer and birds and trees and everything. I thought nothing would grow in that radiation exclusion area that you showed.
Yeah, there's
Was
been a
that a
PBS.
surprise?
The public
Yeah.
television has also had a
Right, maybe I
series,
saw it on that one.
and they are returning.
Yeah.
They seem to be healthy.
Right. Right. Because I remember back in the 60s when I was starting in my research, we wanted to look at the effects of radiation on reproduction. So we knew that they had effects back then. And then to see these animals just looking normal and healthy was the biggest surprise to me. And I guess to everybody. Don't
Yes.
expect anything.
Okay, thank you. Bob Bernstein on Zoom, go ahead.
Hi. First, a safety question. The St. Lucie nuclear power plant south of Fort Pierce is built on a barrier island. That seems like it would be of concern, particularly given global climate change and stronger storms. What do you think of the siting of that plant?
In the beginning, when we started putting nuclear plants all over the place, the siting was not carefully considered. They have some out in California that are in the earthquake zone. They're shutting a lot of those down, but it will be difficult to protect the reactor. You can have possibly, there won't be a tsunami, I don't think, but there'll be hurricanes and there could be flooding. They're designed to safely be shut down. We can hope.
Thank you.
I just want to make a comment or a little story. I traveled on a Russian nuclear icebreaker several years ago, and they took us on a tour of the engine room. And it was the chief engineer who was taking us around. And he said, well, you can take pictures of everything but the control panel. All right, so we were not going to take pictures of control panel. And I asked him, he was taking us around and talking. I said, don't you wear a film badge? Where is your film badge or some kind of a control badge? Oh, he said, I have it, but it's up in my cabin. Well, that's good. So to satisfy me, there was another gentleman there. I think he was the one who was looking at the control panel, and he called this guy up. He said, well, Sergey, or whatever was his name, do you have a film badge or something measuring me that measures the radioactivity. He started looking, reaches into his pocket, under his knees, pulls out something. Yeah, he said, here it is. I have it. So that's security,
Yeah.
of course. And of course, none of the passengers had to wear anything. Well, I was not worried. Obviously, otherwise I wouldn't have been on that one.
We wore film badges on our web belt. So whenever we put on our uniform, whatever uniform we were wearing, our poopy suits or our khakis or whatever, our film badge was put right here. And if we were going to go into the reactor compartment when it was shut down for any reason whatsoever, we also wore a pocket dosimeter, which could be immediately read either by the person looking at it, and they were given a limit of how much radioactivity they could incur while being in the reactor compartment, and they had to leave at that point. But the hospital corpsman on the submarine was in charge of doing the development of the film badges and reporting the results. And I can go into my Navy records, and probably Will can too, and see how much total radiation I received while serving in nuclear submarines. And I would say it was less than 500 millirem. So we were not allowed to have more radiation exposure than you would get from flying in a transcontinental airplane.
There was one other question here, and I'm not sure, wait, on Zoom, if you answered it. It says, reactors on subs are obviously small. Can't such designs be used for distributed energy production? Did you answer that already?
No, but the submarine reactors they're small. We only need enough power to run our electricity and the main propulsion. So the reactors that I was on were about 30 megawatts thermal. We had 15,000 shaft horsepower. And to put that in perspective, when I toured the steam coal power plants in Crystal River, their main feed pump was a 15,000 shaft horsepower feed pump, the same as we had connected to our main screw on the submarine. The newer reactors, I think, are more like 60 megawatts thermal, and the Los Angeles class, I would guess, is probably close to 30,000 shaft horsepower. And
Okay, thank you.
I think you answered part of my question. When I was in California, I saw a lot of aircraft carriers parked right out on the basin. They could produce enough power to supply all of San Diego and all the surrounding areas, but you just said that they just weren't big enough in the submarine.
well, the aircraft carriers had more power. I don't know what their current, do you know, Will, what their power is?
No, but the Nimitz class carrier can produce a lot of power.
Yeah, and they have gone to Indonesia. I guess they had a big earthquake a few years ago and sent the aircraft carrier over there, and they can connect up to shore power and provide electricity to shore power. And they have a lot of it. If they're not running their steam generators to fly airplanes and do a lot of other electrical work, they have a lot of excess electricity powered through there. They have 4 engine rooms, 4 reactors typically, and each one has an electrical generator plant attached and a lot of extra power.
Is that a new record, Julianne?
No. But there's just a comment from Alice Gridley. She says, thank you. Would appreciate if you'd give us an update in the future on Crystal River.
Okay,
Nuclear
Crystal River is shut down forever. That's the update.
Okay.
Thank you, everybody, for
Thank you,
sticking with me.
everyone. Great job, dynamic duo.